All right, folks, it's Bass Action, back in action here. In this video, we are going to go through graphing vectors. We're also going to look at magnitude of vectors, and we're going to get an understanding of position vectors. Now, we're going to kind of combine all of these and actually give a preview into the addition and subtraction of vectors that we'll do in the following video. So let's jump into graphing vectors up here at the top, okay? We've got a couple vectors here. Just as a reminder, this is our initial point and a terminal point because the arrow gives us the direction. So I've got three different vectors here, and on the first problem that we want to do, we want to graph a new vector that would be 2v plus 1 of the w vectors. So what we're going to do is we're going to look at this grid right here and notice that there's not an XY axis. So we can actually choose any point in this grid that we want. With a little experience, you get a little better at kind of predicting where you want to start your graph. But I, of course, already have this graphed, so I'm going to choose a point right here. Okay, so I'm going to make that my initial point, and I want to graph 2 of v first. Now, when I look at the v, I'm going to go over 3 and up 2. So when I'm looking at this, I've got my initial point, and I'm going to go over 3, and then I'm going to go up 2. Now, that would represent one of the v's. I want to do that again. I want to go over 3, and I want to go up 2. Now, normally we wouldn't write these dots. I'm just graphing them so that you can kind of visualize what's happening. The next thing that I want to do is I want to graph one of the w. So the w is going to go over 2 and down 2. So from my current position, I'm going to go over 2 and I'm going to go down 2. And this is now going to be my final point, my terminal point. So my new vector is this right here. Now I don't have a straight edge. If you had a straight edge, you'd be able to draw it better. This is going to represent 2v plus w. Now, we're going to go ahead and do this one more time. We're going to graph a 3w minus u. So this time we want to do 3 of this w. So we're going to go over 2 and down 2. And again, you can technically choose any place you want. Since I already have mine graphed, I'm going to start mine up here because I have a little bit more, foresight as to where this is going to go. So I'm going to go over 2 and I'm going to go down 2. And I'm going to go over 2 and I'm going to go down 2. And I'm going to go over 2 and I'm going to go down 2. So that would represent the 3w. Now, this one's important. I want to subtract a u. So when I look at my u, the u is over 1 and up 3, but I want to do the opposite of that. So I'm going to go back 1 and down 3 when I do that u. So I'm going to go back 1 and I'm going to go down 3, and that's going to get me to my new location. So if I connect my initial point to my terminal point, this right here represents 3w minus v. So if you're just asked to graph, this is all that you need to do. Now, the magnitude of a vector, we talked about this, I believe, in the other video. The magnitude of a vector is going to represent the length. So this is just what we think it is, length. Now, we're going to denote the magnitude, and we're going to use these little double vertical bars, not quite like parallel. They're going to be straight up and down, and then the vector name, and then those double vertical bars. Now, length is going to be a distance. I'm going to come back to that formula over there in just a moment, and will always be positive, okay, just like we've always been doing. So when we look at this length, we can see that, oh, that looks just like the Pythagorean theorem, and that's because length distance is the same as the Pythagorean theorem. So when we are asked to find the magnitude, in this example 2, of these two vectors, what we want to do is we want to think about how can we do this maybe a little algebraically to understand how to represent this. So what I want you to do is I want you to take a look at this vector up here, and this is our new vector. How far over did we go? We went 1, 2, 3, 4, 5, 6, 7, 8. So our new vector is going to go over 8. This is a new notation, and it's going to go up 2. So this would be a way to represent our new vector. When we look at this vector here, we can see that we're going to go 1, 2, 3, 4, 5. Yep, we're going to go over 5. I just had to make sure I was counting that right. So we're going to go over 5, and then if you count how much it's going down, it's going down a -9. Now, what we want to understand, and this is a preview to the next video, is how could we get these numbers if we hadn't fully graphed it? Well, if we take a look at the original vectors that we have up here, Our original vectors could have been written, let's say, as a 3, 2, and our w could have been written as a 2, -2, and we're using these little, look like greater than and less than symbols as our brackets instead, and our u would be 1, 3, with, again, these little greater than, less than looking signs on the ends. So if we wanted to find this without graphing, our 2v, we would take our v and we would multiply each of those values by 2, so we'd have a 6 and a 4, and then our w, of course, is going to just be our 2 and our -2. And if you take a look at this, 6 plus 2 gave us the 8, and the 4 minus 2 gives us the 2. Now, of course, the magnitude of this new vector z, use our new notation, our magnitude is just going to be our new value squared plus our other new value squared. So we're going to have a 64 plus a 4 is going to give us a magnitude of 68. We can repeat the process over here. So let's think about, where did this 5, -9 come from? Well, it was 3w. So let's rewrite our w vector as a 6 and a -6, and then minus our u vector, which was our 1, 3. So now we're going to do our 6 minus our 1 gives us our 5, and our -6 minus our 3 gives us a -9. So our magnitude of this vector is going to also be pretty straightforward. Using that new notation, we're going to have the square root of a 25 plus an 81 is going to give us a magnitude of 106. Okay? Now, a position vector is essentially what I just found up there above. Okay? So a position vector, okay, has two different kind of ways that we can think about this. So our algebraic vector is what I was doing up above, and it's denoted this AB, okay, where A and B are real numbers. These real numbers in the world of vectors are called scalars, okay, just a fancy word for a real number, okay. Now, the position vector assumes that the initial point is at 0, 0, okay, and the terminal point is wherever AB is. So what I did up here was essentially creating a new position vector, okay? So this right here is our position vector. So what I wrote here is actually called the position vector. I just helped us find it before I gave you the word for it. So our position vector is the point, or is the vector 8, 2, and our position vector over here, we already found it, is going to be this vector 5, -9. Now we've got one more thing that we can think about in terms of our vectors and writing them, and we have another form, and it's called a component form. And a component form is going to look like this. We're going to take that A and B, but we're going to make them coefficients on a term with an I and a term with a J. So we can take this exact same vector for Z, and we're going to now write it as A 8I, and we're going to say plus 2J, okay? So now we're just going to have an I coefficient, or a coefficient on the I component and a coefficient on the J component. We can do the same thing over here. We can write this in its component form, and its component form would be 5I, and now it's going to be a minus 9J. Okay, so those would be our component forms. And you do need to be comfortable with the component form and with this algebraic form, okay? So be comfortable with both of those. Now down here is our addition and our subtraction formulas. This is actually what I already did up above. When we wanted to add two vectors, we added the A components to get a new A component, and we added the B components to get a new B component. The exact same thing when we had a scalar times our vector, we just multiplied that scalar times the A and the scalar times the B. So it's exactly what I did up above on those problems. So just be comfortable when you're thinking about this, be comfortable with how you would graph them, and then how to find magnitudes and understanding the difference between an algebraic form and a component form.